Hi, in this video we're going to look at the process of reversing the chain rule through integration. Now, if you remember from last year, the chain rule is used when we are dealing with a composite function, and we can see the formula for it here written on the screen. So if I've got a function f of g of x, and I want to find the derivative of that with respect to x, then I go and take the derivative of the part inside there first of all. That's going to be g dash of x. And then I take the derivative of f and just leave the g of x as it was. And that is what we refer to as the chain rule. If I do it on this example over here, x squared plus 2x all raised to the power 3, if I want to derive that, well, first of all, I take the derivative of x squared plus 2x. That's going to give me this bracket over here, 2x plus 3. And then I'm going to go and take the derivative of something raised to the power 3. Something raised to the power 3, well, I'll get a 3 down in the front, and the power is going to diminish by 1 to 2. I'm going to leave the bracket x squared plus 2x at the end there. And when I do that, I'm going to end up with something that looks like this. It's going to be 3 brackets. Well, in fact, I could take out 2 from that first bracket, couldn't I? I'm going to end up with 6 brackets x plus 1 times x squared plus 2x. I've got a product of terms. In fact, if I kept it as it was, if I kept it like this, then I can see that there is this link here between this bracket and that bracket. This bracket being the derivative of the first bracket being the derivative of the second bracket. And this is what you've got to look out for. So if you come up with an integration where you are dealing with a product, then one of the questions you're going to have to ask yourself is this a case of reversing the chain rule? Because if I'm going to look at the integral of a derivative of g times by derivative of f, working on the function g, then the integral of that's simply going to be f of g of x plus c. So if you have to integrate a product, check if one of the factors is the derivative of the other. So let's take this example here to begin with. Give a bit more space so we can work that through. Well, we can see straight away that we've got a 5 out the front. No, I don't want blue, I want black. I've got a 5 out the front, so I'm going to drop that in front of the integral sign. And then I've got this. I've got 8x to the power 7, and then the bracket x to the power 8 plus 1 raised to the power 4. It is a product, and this thing here is the derivative of what I've got inside the bracket. Now, in order to help you through this, it's sometimes useful to use a bit of a substitution here. So I could say let x to the 8 plus 1 equal a. Then I know that dA dx is going to be 8x to the power 7. And if I rearrange that, I can say that dA is going to be 8x to the power 7 dx. Now, having made this substitute, or having set up this substitution, if I now go and look at my integral, what have I got? I've got x to the power 8 plus 1. That's going to be a. That's being raised to the power 4. And then I've got 8x to the power 7 dx. 8x to the power 7 dx is dA. And so now I've got a function that's simply in terms of a. I can take the integral of this. It's going to be 5. A is going to have the power of 5. and I'm going to divide it by 5, and I'm going to have the letter C afterwards. And then all I have to do is go and substitute back in again. And what have I got? Well, I've got, not 8, I've got x to the power 8 plus 1 raised to the power 5 plus c. The two 5s are going to cancel one another out. And there is my original function, the one that was derived in order to give me that product. As I say, a substitution can be really useful to help simplify this process. Here's one that's a little bit more complicated, but again, make a simple substitution. Let the thing that is going to be derived be the thing that you substitute. So 2x minus 3 is the derivative of that larger bracket. So I'm going to let a equal that larger bracket, x squared minus 3x plus 5. That means dA dx is going to be 2x minus 3. 2x minus 3 is the bracket that I've got over there at the front, so it looks as though I'm on the right track. Again, just rearranging this, I can say that dA is going to be 2x minus 3 dx. And that means this integral can now be rewritten as the integral of, instead of x squared minus 3x plus 5, I can write the letter a to the power 4, and instead of writing dx and the 2x minus 3, I'm going to write dA. I'm going to get a to the power 5 divided by 5, and then add c onto it. And so I'm going to end up now with an integral that's going to be x squared minus 3x plus 5 raised to the power 5 divided by 5 with c added to the end of it. Right, so now going to our last example. This is at the integral of e to the sine x cos x dx. Well, hopefully by now you'll know and understand and recognize that sine and cos are related to one another. One's the derivative of the other. So I'm going to start off and, oopsie, get my pen going. I'm going to start off and say let sine x equal, I don't know, some variable, let's call it t. So dt dx is going to be cos x. And so dt is going to be cos x dx. Now going back to the original integral, what do I have? I have the integral of e to the power t. Cos x dx I can write as dt. So now I need to find the integral of e to the power t dt, and that's very simple because e to the power t is simply going to be, the integral of that is simply going to be e to the power t plus c. In other words, I'm going to have e to the power sine x plus c. And there is the integral of that function. Right, hope this makes sense to you. You need to go and practice now. Good luck. Goodbye.